Network of roads in US versus airline network in US. Which one is, are they similar? Are they, I mean, we talked about two types of networks. One is uniform random, or actually it also can be called, the uniform random is a slightly confusing term because what you mean by uniform random is the way you generate the network. The generative model of the network is uniform random. And if you generate it that way, what you actually get is a Poisson distribution which really has exponentially falling tail, right? So these are also called, uniform random networks are also called exponential networks. Okay? And in fact, this is a better term to remember because compared to this, power law basically falls much slower, right? Power law is only falling polynomially, whereas exponential network is falling exponentially. Okay, so here's the question, just what do you think, which one, the network of roads in US versus network of the airline network, okay, passenger airline network, which one is which? Are they both the same? Are they different? Have you thought about this?
Well, the road network isn't uniform random because any 2 points aren't likely to have a connection between them.
No, but what I'm saying is, if you look at the full network, okay, is the road network more like the exponential network or more like the power law network? Forget about how they were generated, okay, because in fact once you see the network, there are many different ways. In fact, last class, at the end of last class, we said there are at least 2 different ways of generating a power law network. One is copying other people's pages and removing some of the links. The other is just with higher probability putting links to already popular people. Okay, so there are many possible local generative models that will finally end up in what looks like a power law network. And similarly, there can be many possible ways in which you can actually wind up getting an exponential network. So my only question is, if you look at the network of roads versus network of airports in US, are both exponential, are both power law, or there's really nothing much you can say? What?
Both are power law.
What?
Both are power law.
Which one? Roads are power law. Both are power law. Okay. So one answer is both are power law apparently. Now, which one do you think is likely to have a higher claim for being a power law network? One point about power law networks, remember, is rare events are not so rare. Okay, so that basically means highly connected nodes are not so rare. Do you get to see more of highly connected nodes in the airline networks or in the road networks? What?
Airlines.
Airlines. Right? Why? Because what are those evil things called? You all paid for it. Right? Basically, if you want to go from Phoenix to Tucson, sometimes you'll go to Toronto and come back. Because Toronto is the hub for this airline. Okay? It's the hub system. That's what kills you eventually. Okay? So Atlanta is the world's most, the most frequented or most congested airport. Why? Because Delta has a hub there. So Delta wants to go from place A to place B, it'll always find a way to go to Atlanta. Because that's the easiest way for them to schedule the flights. Okay? So clearly, if you actually look at the networks, this is the road network in US. I mean, I'm talking about big roads, okay, the major interstates, okay? And here is the airline network in US. Okay, you can almost see, if you look at the airline network, that it's full of hubs. There are several, I mean not full of hubs, and there are many more highly connected nodes in the airline network. Okay, so in fact, I would say that this road network is closer to being an exponential network, and this is more of a power law or a scale-free network. Now, suppose you want to bring down the system. I'm not teaching you how to bring down systems, but suppose you want to bring down the system. Which system would you think would be easier to bring down? What? Say it loud. Scale-free ones. Because all you need to take up, if you want to bring delta down to its knees, all you need to do is, kiss your girlfriend goodbye when she's leaving in Atlanta, right? And then, they'll close the airline, airport for like 3 or 4 hours, and then deltas, every flight gets delayed, right? Whereas if you kiss your girlfriend or boyfriend goodbye on the I-60, what happens? Several people will honk at you, but the world doesn't come to a standstill. Okay? Now, a different issue is if I am, so this is basically if I want to bring the network down. If I want to bring the network down, then power law networks are easier to bring down than exponential networks. On the other hand, if you are having random perturbations to the network, right? Then the question is, which one, so if as the amount of perturbation increases, which network is going to get affected almost proportional to the amount of perturbation? And which one is likely to be reasonably unscathed? So for example, if randomly, so random things like, for example, meteors keep falling from the sky, and they fall on some, either a road or an airline, an airport, and that airport gets closed or that road gets closed. Okay, and increasing the amount of perturbation means the number of meteors that are falling. Right? So which one do you think, which of these networks, so if I were to draw the number of meteors falling on this side and the percentage of nodes getting disconnected, on this side, where the meteors, I assume, I'll hope that meteors don't have anything against us. Okay, they're just falling, they're doing their job. Okay, they're just randomly falling. Okay, so if this is the case, which of these networks is going to be affected more? So presumably, as the number of meteors increase, presumably you would assume that the perturbation, the disturbance to the network increases. Which network is going to be disturbed less?
Less is exponential, more is.
So in fact, interestingly, the chance that if meteors are falling, okay, unless they fall on Atlanta or New York or Phoenix, they're not going to shut down airlines. Falling on Cedar Rapids or Tucson Airport, nothing is going to change. Okay? Do you see what I'm saying? Whereas, so as the number of meteors increase, the disturbance caused to the road network more or less sort of proportionally increases. Okay? On the other hand, disturbance caused to the scale-free network is much less. So for most of the time, it may actually not change at all. Unless the big guys get affected, nothing changes. Okay? So the point about this picture really is that we actually learned something interesting about attacks versus disruptions on scale-free versus random networks. Okay? So a disruption is just a random percentage of nodes are removed because randomly meteors are falling on various nodes. And they're just removing that node from the network. The question is, how much of the network is getting disconnected? What fraction of the paths are getting disconnected? Okay, and in particular, what you're interested in is the diameter of the network. How is the diameter of the network changing? The diameter, of course, is the longest geodesic path between any two connected nodes. Okay, it's what we argued basically is that it increases, the diameter increases monotonically and pretty much linearly on the exponential networks, which are basically uniform random networks. Okay, but it more or less is unaffected for scale-free networks, because unless this random event winds up knocking down Atlanta or in the web scenarios Google, nothing really happens. So for random changes, exponential networks are less robust than scale-free networks. Okay, which is sort of the reason why, in fact, delta, apart from other efficiencies, delta basically starts having hubs. Because one hub, it's easier to take care of. Okay. On the other hand, if you are attacking the network, then you know the network. You know what are the hubs in the network. And you know what are the highly connected nodes in the network. And all you need to do is take them out. The moment you take them out, then it makes a huge, big difference. Okay? There is not too much you can do to attack a random network, because everybody is just as good as everybody else. And so, there is not too much thinking to do to say which node am I going to take out. Basically, they're all about the same. Okay? This is a socialist country, right? Because most of the people would be in the median and then away from the mean. I'm sorry, in the mean and away from the mean, things fall exponentially down. Okay, powerlaw networks is the societies we live in, where there are a reasonable number of rich people. Okay, so you can kidnap people here and actually they'll pay huge ransoms. There's not too much point in kidnapping people here because nobody has any money. They're all approximately the same. At least there's no difference in kidnapping one person versus another person. Taking down one node versus another node. Okay, so this is kind of interesting to realize that they have these separate trade-offs, with respect to disruptions versus attacks. Okay, that's a useful thing to know. Even though we actually did not, we were in this mostly for search, which we'll get back to, search over social networks, etc. But since we are talking about networks, we can also talk about robustness with respect to networks, with respect to disruptions. Okay. By the way, this picture that I have here, this is, in fact, I added a new paper to the readings list on networks. And in fact, previously there were like a series of small articles. There is an article now that I added. It's a tutorial article on scale-free and small world networks. And that would be the main reading for you. If you want to read something outside of that. Okay. So that's from that actually. One other thing, of course, we got into this whole discussion about networks, about powerlaw networks, because we were trying to explain small world phenomena, right? And then we knew that small world phenomena will exist in random networks as long as the average degree is more than 1. Okay, but then we couldn't convince ourselves that the networks, the social networks, are random networks. They seem more like powerlaw networks. Okay, that's what we convince ourselves. Now the question, of course, is, will small world phenomena go away in powerlaw networks? It turns out small world phenomena exist also in powerlaw networks. Okay, in fact, there's a whole bunch of literature on this. But for example, for the web graph, I forget the citation on this, but average path length on the web graph is about this 0.35 plus log n. And since the average path length is logarithmic in the size of the network, it is in fact a small world. Okay, and in fact you can also theoretically prove that if you have a powerlaw network generated from either the copy model or the rich getting richer model, you will indeed have small world phenomena. Okay, so this is sort of a tying up the loose ends. We got into this whole thing because of the small world phenomena, but they will hold even in powerlaw networks. It's just that powerlaw networks have different properties, especially with respect to attacks versus disruptions. Okay, and you should know what is a powerlaw network and what is not a powerlaw network. For example, if the world is exponential network, I mean, if the web is an exponential network, do you think it would have made sense to do PageRank style analysis? No. If everybody is about the same, then what's the point in saying who is bigger than who? Right? In fact, it's only because the web network is a powerlaw network that there are enough people who get, the high page ranks. If all of the entire web basically gets page rank of like 0.000000001, and there's only like one node maybe or so which gets higher than that, then it's not interesting, because then basically, remember, the whole reason for PageRank analysis or the link analysis was to see among the million pages that seem to be having the same level of similarity to the query, which of them are more important than the others. Okay, and this extra importance you're trying to find by links. Now, if you are an exponential network, pretty much most of them will have the same level of importance. Okay, so in a way, actually, much of this discussion here on the powerlaw networks is actually explaining to you why, in fact, importance analysis even worked in the world you are living in. You take it for granted in the world you live in that there are more important people, less important people. That's because your world is this, not this. If your world is this, there is no point in doing link analysis. Okay, so that's the kind of the background on this. Okay, one thing before we move on from the networks is actually an interesting point about all these social networks, especially the human social networks, and especially before the advent of centralized databases of networks, is how to navigate a network using only local decisions. Okay, the idea is that you normally know who your friends are, hopefully, but you have no clue as to who your friends are. And you definitely have no clue as to whose friends are. Okay, so if you're trying to figure out, if you're trying to do this Milgram experiment where you are trying to send, a letter to, let's say, somebody in, some stockbroker in Boston, you are trying to figure out among your friends that you know who is most likely to be able to get this letter to that end person with the fewest number of hops. Okay, and you don't have the entire network in front of you, so you don't actually know which of your neighbors are the best neighbors for this particular task. Okay, so the challenge of social networks in normal life is navigation. How do you navigate your social network efficiently? And there is actually a large amount of work on navigation of social networks by local decisions. And it's very fascinating, but I'm not going to go into much of it anyway, because for the web scenario, social networks don't need to be navigated locally. Facebook has the entire social network of all the Facebook people in front of it. Okay, so it knows here you are, here is somebody else, so it can just do a graph search on that graph. Okay, so on the web, essentially, you have centralized access to the network structure. Of course, LinkedIn, Facebook, etc. try to not give you access to the entire network. But they have access to it, all right? Right? And in fact, they can do a lot more analysis on the entire network that they have access to. Okay? So, in some sense, the navigation in the small world, in the networks, local navigation of the networks becomes less important in the web applications of social networks. Okay? Of course, this, as I said, this is what we normally think of, which is among the people I know, who should I entrust this letter to so that it will find its way to the right person. Okay, there is a bunch of, so of course there are, even if you're doing this, you can actually, here is like a dumb idea. Let's start with the dumb idea. If you're doing local search, if you're trying to decide how to get this letter to the broker, okay, you do the chain mail, which is basically you make copies of this letter, okay, 1800 copies of this letter, and give it to all your 1800 friends, and ask them to make 1800 copies of this letter and send it to their friends. And hopefully at the end of this, you're basically broadcasting to the network, and the stockbroker will get it eventually. Okay. Now, of course, this is possible, and the real problem, of course, is that this will eventually it will just clog the network because there's just too much broadcast going on, too many different messages being passed around. And of course, in the human terms, you would just stop looking at the chain mails. Okay. The more interesting question, of course, is if I'm going to give it only to one of my friends or two of my friends, which friends should I do? That's a much more interesting question. There are some references, some links from the readings list if you're interested in that. Okay, as to how to, under what conditions are small world networks efficiently navigatable with just local decisions. But much of that is sort of a moot point for the web applications because you have the entire database. In fact, about the only time you cannot do an access to the entire database is, remember Napster? You can admit it, it's okay, I'm not going to turn you in. So Napster had a centralized database. So they could bring it down. They basically sued the Napster. So now, of course, all these torrent sites, they don't have centralized databases. They have peer-to-peer systems. So the network connectivity is spread over many more nodes. Okay, in those cases, in fact, one place, these approaches are still very interesting as to what's the best way to broadcast in a peer-to-peer system so that you will go from one place to another place. That's one place where it is useful. That's the point I was making, that unless centralization is banned, Napster got banned because centralization was, was getting them into legal problems. Okay, but Facebook is still not banned. Facebook has your entire social network, and if I have the entire social network, at least from that point of view, the problems are massive. Okay. Okay, so summary of all our discussion about networks, and after this summary, then we'll go into some applications of this back to web search, which is where we got into, right? So of course, a network. We talked about small world phenomena. We talked about uniform random networks, which are also called exponential networks. We found that most real world networks are not actually exponential networks. Some are, but many aren't. And the other ones are more like powerlaw networks, okay, which basically, in the case of powerlaw, essentially, powerlaw networks are also, as I said, they have many names. One is long tail networks, the other is heavy tail. And both long tail and heavy tail, it turns out, are actually adjectives not for networks, but for distributions. This whole thing was in terms of the probability distributions. Okay, the degree distribution in a uniform random network is a Poisson distribution which falls exponentially, and the degree distribution in more normal networks, in the powerlaw networks, essentially falls polynomially. Okay, a distribution that falls polynomially, interestingly enough, for the longest time, people never actually handled distributions that fall polynomially. Okay, because in some sense, it's much harder to get the area under the distribution to be finite, especially if it's falling only, like as I say, if you're falling at, remember it's k power minus r, and if r is 1, then it's a harmonic series. It doesn't even actually become 1 under that term. Okay, so most people, in most cases, people will just assume an exponential distribution about anything under consideration. And heavy tail distributions actually have become very interesting. Once people realized that in many phenomena, actually the rare events are not that rare after all, then you start looking at these polynomial distributions. Okay, a completely different example of a different use of this heavy tail distribution actually occurs in search scenarios. Okay, in search scenarios. So consider the following situation. Suppose you have a big graph. I mean, you're all computer science students, right? You have a big graph, and you're trying to find a path between one node and some other node. Okay, and you're trying to find the optimal path. So suppose you started searching for the path. Okay, you didn't find the solution right away. Now the question is, if I tell you, so you spent already half an hour searching for the solution. Okay, now the question is, should I continue going in that direction, or should I start all over again and look for a completely different random direction? It turns out that if I were to tell you that, you know, there are easy ways of solving this problem. There are enough easy ways of solving this problem. Then what would you do? You would just basically restart all over again, try to look for a different direction. Okay, this sort of random restart search would work to the extent the number of solutions are heavy-tailed. That means number of solutions of different difficulty are not exponentially distributed but polynomially distributed in terms of their rareness. Okay, and in many problems, in fact, it turns out, in many combinatorial problems, it turns out that the solutions are distributed, the solution distribution itself is heavy-tailed. And because it's heavy-tailed, it's like, I don't need to tell you. You can just think after a while, you know, there must be an easier way of doing it. Let me go to the top and look at completely different random direction. Believe it or not, random restart searches have been shown to be very effective for large-scale constraint satisfaction problems, for example. And the reason that is the case is because heavy-tail distribution holds for solutions. Okay? Again, the point I was making is the long tail and heavy tail, they're all about the distributions. In this case, for the networks, it's the distribution of the degree. It could be, and in the case of Zipfian distribution that we were talking about a couple of classes back, that's about the frequency of words in a corpus. Okay? And then finally, just now I talked about the rareness of solutions of different levels of difficulty for the same problem. Okay, and then we also talked about the issues of navigation, and we talked about the difference between powerlaw networks and uniform random networks in terms of random perturbation versus adversarial attack. Okay, so that's the summary. So let's talk about some applications for this. So first of all, as I said, in fact, many of the things you're already doing without knowing social networks and powerlaw networks were actually working because you were in a powerlaw network. That was my point, that page rank analysis would have been completely useless if everybody has the same page rank. Right? Which is what more or less will happen if you have if the web network is a exponential network. Okay. Now, so that's one thing, and then if you have access to the social networks, you can talk about finding communities. That means near clicks in the social network graph to see, and then if you do find a community, you can try to find out why are they having these many links between them. Okay, so that's another approach. That's another use for social networks. Now, the two ones that I want to actually talk about in today's class is one, if I have access to a social network, as I mentioned a couple of days back, I think a couple of classes back, you can do social search, which is, I have a question, which of my friends or friends of friends of friends would actually probably be competent to answer it and be willing to answer it. Okay? Their competence in answering my question depends on whether or not the topic of the question is something related to their expertise. Their willingness to answer depends on how close they are in the social network. Presumably my friends will give me the time of the day. My friends might or might not. My friends say, what the heck are you wasting my time for? Okay, just because I have the answer, I don't have to give it to you, right? Unless, I owe you something, you're my friend or you're my friend's friend. I don't need to give you the answer just because I have it. Because we have other things to do in our lives rather than taking care of everybody's questions. Okay, so Aardvark, which we'll be talking about in a minute, basically tries to support this notion of social search. If I have access to the social network, then I will try to find you a person in your social network. Okay, remember, you may yourself don't know, you may yourself not know your entire social network, but Facebook knows it. You know your friends, and Facebook knows the friends. And it can introduce you to them when you actually have a question and say, you know, would you like to answer this guy's question? Okay, so that's Aardvark, and I think it's a very nice idea. It's an easy idea also to understand, so I'll just explain that. And as I said, it's now part of Google apparently as of this month. And then we will also talk about this notion of trust. And one other interesting thing about social networks is you tend to trust people you know. And you tend to trust people who are trusted by people you know. Okay, so you can analyze trust by having access to the social network, and you can then start doing search which is sensitive to trustworthiness of a page. Okay, so this one is about still pages, this one is about actually finding humans. Okay, here you're trying to find a human who will answer your question. Here you're trying to find among all the pages, which of the pages which actually has similarity to the query is also trustworthy. Okay, and you know that you could do it in a social network of pages where you start with some trustworthy pages, and then basically all of us might say Wikipedia is a trustworthy page. Okay, or New York Times is a trustworthy page. And then if Wikipedia is putting a link to some other pages, then those pages transitively are trustworthy. Okay, if I believe that Wikipedia is 1.0 trustworthy and Wikipedia sends 1,000 links to 1,000 pages, then it's reasonable to assume that all of those get 1 over 1,000 trustworthiness. And furthermore, you can also talk about attenuation of trust. Okay, you know that you trust the people that you know, and the people that are trusted by these people, you trust them but less, because you don't quite know why, you know, as the distance grows, the level of trust attenuates. And we will look at how that can be used to consider a variation of page rank called TrustRank. Okay, and remember when I talked about page rank, I said the entire source of ideas for changing page rank such that it will do more interesting things is what? What do you play with? What? What? Say it loud. What do you play with? You know, remember page rank, computation. What? Reset distribution. Play with the reset distribution. So the whole point is, in this idea, you know, remember in the page, you know, in the topic specific page rank, we wound up having a different reset distribution for each topic. And so each page had a whole set of page ranks. One for sports, one for science, one for politics. And when a query came, you computed the probability that this query corresponds to each of these topics. And you weighted that topic's page rank of that page. You took the weighted summation of the various, you know, page ranks of the page. Okay, that's what you did. Now, when we do TrustRank, what we will do essentially is we'll make a trustworthy, a reset matrix, a reset distribution, which is sensitive to trustworthiness of the page. That's it. And that will just basically, everything else remains the same, except now the eventual eigenvector that you get is going to be sensitive to the initial trustworthiness. I mean, the reset trustworthiness of each page. Not initial, but if you don't have anything else to do, where are you likely to go to? Probably Wikipedia, probably New York Times, because you think they are trustworthy pages. Okay, so that's the idea we'll talk about. So I kind of, you know, those are the two things we'll do. And both of them essentially are using social network ideas. Of course, this one, which we already completed discussion, was using social network ideas anyway. Okay. Okay, so actually, I mean, I'm not sure whether you really need a sort of a motivation as to why search should be sensitive to trustworthiness of a page in general. But obviously, if you don't, here is and if you do need a motivation, then obviously there is a large amount of spam going on, large amount of untrustworthy sources, large amount of adversarial sources, and so it's not enough to know that the answer is, to know that the page has an answer, but you need to know whether the answer is actually trustworthy. Because as we mentioned earlier, one time back, and in fact this is one of my questions too, in the blog, which is, relevance is something you can tell. Okay, so if you ask who is the director of Godfather, and the page says the cost of 1 pound of tomatoes is $3.25, you know it's irrelevant. Because your question is about, director of Godfather, and the page is talking about cost of tomatoes. You know that it's irrelevant. Okay? But if the page says the director of Godfather is Woody Allen, unless you're testing the page, how would you know whether it is telling the right thing or wrong thing? It's clearly a relevant answer. But is it trustworthy? You have no idea. So trust is something that should better be there already for different reasons. Okay? By the time the answer comes, you can't tell whether or not it's right. You have to take it on trust. Okay? So it's useful, given the adversarial nature and given the amount of spam in the world, it's useful to actually use trust analysis. And trusts are normally in human societies, trust propagates on social networks. You trust your friends, and if your friends trust somebody, then you probably trust them too, but not as much. Okay, and if your friends distrust somebody, you probably will distrust that somebody too. If you distrust somebody who then distrusts somebody, all bets are off as to what you would do to this third person. Because is the enemy of your enemy your friend or not, or enemy? I don't know. Because it depends on the context. But normally trust is transitive, distrust is not. That's the bigger point. And trust is transitive on the social network. That's what you do. By the way, background. What's the background of this slide? There's like an image there. What's that image? Where does the word spam come from? Yeah, but I mean, you eat spam? So why did spam come in? Why is it that of all the words in the English language, why did spam get associated with spam mail, spam stuff, etc.? Yes, sir?
Monty Python?
Yes, Monty Python. And how many, obviously you are the only guy who saw the Monty Python spam sketch. 3 points for you. But the rest of you should watch spam sketch on Monty Python. Just say spam sketch Monty Python on YouTube and you will see as to why indeed spam is a, in fact that's really the place where it actually, on the internet, spam mail, everything has the word spam associated with it. It's true that I'm a vegetarian, so I can't quite tell you whether spam is good to eat or bad to eat. But I do know that they made it with mass scale to send it to, I think, Second World War or First World War soldiers. And its advantage is that it was almost indestructible. I mean, it can't be eaten, it also spoil. Okay, so they were just sending it in cans all over the place. But, anyway, that's where the word spam got associated. The Monty Python sketch is really the word that where the spam got associated. I'm just surprised at total lack of general knowledge in this class. But anyway. Okay, so now this point here essentially is repeating what I just said earlier, which is that a powerful way we avoid spam in our physical world is by preferring interactions with trusted partners. That's what you do. Okay? I mean, the world is adversarial. It's not just that web is adversarial. The world you live in is adversarial. Okay? And it's full of spam. And it's full of untrustworthy people. Now, the interesting thing is we just reduce the interactions to only people who we think we trust. Okay? And that's one way you reduce it. Now, you can trust is propagated over social networks. So, here is the knock-knock joke version of it. Okay, it basically says knock knock, who's there, Aardvark, okay, open door. It's not funny. Okay, even if you are into knock knock jokes, it's not funny. Right? Where's the punchline? So what you're supposed to do when somebody knocks on the door is Aardvark who? You want to know who is knocking on the door before you open the door. Unless you're from really small town where everybody trusts everybody, when somebody knocks on your door, you first ask who is it? Right? So that's where you ask Aardvark who, and then of course you get a nice knock-knock joke. But the point I'm trying to make is every interaction in our nice world is mediated by trustworthiness and checking whether or not the person knocking on the door is worth trusting, other than whether or not you're going to let them in. Okay? And these are done, obviously, how you decide to trust somebody is based on social networks. And one of the interesting questions is, trust can also be aggregated, assessed, and used on the cyber world too. Okay? One interesting difference, one interesting question, of course, is, you notice that in most of these eBay sort of things, customers give feedback about a seller, and somebody is making sure that this feedback is, is actually from people who, in fact, bought something from the seller. Okay, and then that kind of becomes a reputation of that particular seller and reputation of that particular buyer. Okay, if this buyer has low reputation, that means they'll bid on this and they won't actually pay up when time comes. And if the seller has low reputation, that means they will, try to sell you this stuff, but it never actually shows up. Enough people are complaining about it. Now, reputation can be thought of as, so if trust is normally user specific, I might trust him, you may probably not trust him. Right? Everybody has somebody who trusts them. Right? Think about the person that you kind of hate, you completely distrust and hate. They also have somebody who trusts them. Okay, Hitler had people who trusted him, right? So does everybody else. Reputation, on the other hand, is an aggregate metric. Okay, trust is a user-centric metric. Reputation is a user population-centric metric. Okay, and most of these opinions or eBay, etc., they are essentially assessing reputations which are aggregated trust over multiple users. Okay. So what we will basically talk about now, so that's one thing. So actually after this we will talk later about TrustRank computation using propagation of trust. But let me see, I think maybe I should just go there first. I'll skip over this, and then let's do this. So since we're talking about trust, one issue is maybe, as I said, you can compute a reset. You can set up a reset matrix for the page rank computation that is sensitive to trust. Okay. Now here you want to think of the links between pages as making up the social network between pages. Okay. Now the question, of course, is how do I set it up? I want to say that when I'm not doing anything, I'm more likely to go hang around in trustworthy pages. Okay. And furthermore, I want to say that trust. So to do this, I need to identify a seed set of pages which are considered trustworthy by most people. Okay, and then from there, any page that is linked to from that page, so any page that is pointed to from a trustworthy page gets some of the trust of the trustworthy page. Right? How many of you have seen Simpsons the movie? Okay, so remember they get Tom Hanks into the middle of the movie. The reason was because apparently Americans believe he is the most trustworthy person. And so then they had to sell this totally made up news as to why they destroyed Springfield. And so they get the trustworthy guy to speak up. Okay? The assumption is a trustworthy person can sell untrustworthy stuff because by default we assume trustworthy people pointing to something means some of their trust attaches to it. Right? Okay, so the issue is have an oracle or a human identify some good pages and also some bad pages on the net, and then you would basically propagate trust from these trustworthy pages to other pages on the net, and enough pages will now have trust numbers, and then normalize their trust numbers into probabilities and set the reset matrix. Do you see what I'm saying? So most pages will have epsilon, and any page which has non-zero trust will have a higher probability of you transitioning them. The highest trustworthy page will have a much higher probability than less trustworthy page. Now, so the assumption is in this kind of a computation, by the way, this is we cannot actually tell whether, for example, Google is using this, but more likely they're not. I would be surprised if it's something that's being used. Okay, because it's again just changing the reset matrix such that you are going to more trustworthy pages more often when you get bored. And that's a very reasonable thing to do. Okay. So the assumption here is that somehow the trustworthy pages point to other trustworthy pages and the bad guys only point to other bad guys. Now the interesting thing about this assumption is that let's say you are in the Middle East, right? You would consider, if you are an Israeli citizen, you might consider certain set of newspapers to be trustworthy. And if you are a, I guess the other side, Palestinian or Arab citizen, you might consider some other type of newspapers to be trustworthy. So from your side, the other guys are bad guys. From their side, these guys are bad guys, to some extent, which is fine. If you just want to hear amplified your view of the world, then basically you can set Israel's Google.Israel might have a separate reset matrix than Google. Whatever, another Aardvark. This is completely possible. Okay, so in terms of the trust propagation, this is something that I already mentioned. Trust is propagated and it attenuates as you go farther and farther. Trust from different sources is normally additive, it adds up, and distrust is difficult to propagate. Okay, and trust versus reputation. Trust is a user-specific metric, reputation is a user population, aggregated metric. This is something that we already mentioned. Okay, now here are some obvious propagation ideas. You can start with the seed pages and give them trust 1. And there are two ideas. One is that trust gets dampened. So if you are now sending k links out, okay, then each of those links will only have beta of your trust propagated, where beta is less than 1. And if you go one more link, it's beta square, one more link, beta cube, and so on. So as you go farther and farther and farther, friend of a friend of a friend of a friend of a friend, you trust them almost close to 0. Okay? The other thing is trust splitting. What you want to do is, if this is 1, and then you want to say beta by 3, beta by 3, beta by 3. Since there are 3 links going up. You've combined those, so you start from the seed pages. You start from the seed pages and you propagate trust this way. Okay, then not only the seed pages have a trust number, but a whole bunch of other pages that are connected to them on the web have trust numbers. At this point, you renormalize these numbers into probabilities. Okay, that's the idea of TrustRank. And all of this is going to just change the reset matrix. Everything else remains exactly the same as before. Okay, so it just changes the probability that if you're not doing anything, the probability that you're going to be on this page is higher than some other random page. One other thing, of course, is the trust. I said trust is cumulative. So, for example, if this guy is getting half trust from this side and 1/3 trust from this side, and these both are trustworthy sides, then you would just essentially assume it's half plus 1/3. Again, a reasonable thing. So if this guy is your friend A's friend, you kind of trust them, but they also are a friend B's friend, then your trust increases. That's more or less what we say. Okay, so if you do this, then you have a pretty reasonable idea for actually doing page rank that is sensitive to trust. Okay. About the only interesting question, if you were to go back and read this paper, what else do they do for the rest of the paper? This idea is already over. Okay, so what do you need to do? You need to do evaluation, but more importantly, you need to talk about the engineering issues as to how many sites are in the seed set. Okay, so what if, for example, I say I trust page 1, page 2, page 3, and page 4. That's it. And it turns out these guys are all isolated. They don't point to anybody. Then you're dead in the water, right? Because trust is not propagating. Okay, so you need to basically find seed pages, those pages that have high out degree. Do you understand what I'm saying? It's not enough to just say, I trust my friend A and I trust my friend B, I trust my friend C. All of them are sociopaths, they don't talk to anybody else. That means my world ends with those three people. Okay? I need to have people who have friends so that trust can be propagated on that social network. So I need to actually get the seed set, which, and how do I get the seed set? Basically, of course, in getting the seed set, and this needs to be labeled. Some humans, have to sit down and say, these are trustworthy, these are not trustworthy. And we are talking about 8 billion pages. And if you just start with 5 or 6 seed pages, it's not going to be enough. So you need a reasonably large number, and it's going to be painful for people to say, yes, this is trustworthy, no, this is not trustworthy among these pages. So you want some fast ways of doing this. And the best idea would be to actually pick, here is one idea, one engineering idea, which is, imagine you did authorities hubs analysis on this graph, on the link graph. Then would you be picking the trustworthy sites from the authorities or the hubs? Not authorities, because authorities don't point to anybody. Hubs are the ones who point to other people. Okay? So if you were to do link analysis, if you were to do authorities hubs, okay, and you have an option of either taking the top 100 authorities or the top 100 hub pages and say, I trust these guys, I don't trust, among the hub pages, these are the hub pages I trust, or among the authorities, these are the authority pages I trust. Clearly, you should go with the hub pages because hub pages actually point to other pages. You see what I'm saying? So, in fact, this is what you really need to do. But if you are doing PageRank, what do you do? One idea is to probably just somehow hope that high PageRank pages also have high out degree. But there is no reason to believe that. Because high PageRank pages only have high in degree. Right? So what you really need is a way of computing hub. But if you are in a PageRank world, you make this idea called inverse PageRank, which is reinvent the wheel of hub authorities, the hub part, and call it inverse PageRank. Where inverse PageRank now is just computed as PageRank, except in terms of focusing on the incoming links, you focus on the outgoing links. Okay, I'm not making this up. This is actually a nice VLDB 2004 paper, and you can read this. But essentially, this is what you need to do because the right thing to do would have been hubs anyway. Just saying I trust these authorities who are strong and silent types is not going to help because these authorities are never going to open their mouth and say these are my other friends. They won't say that. If they don't say nothing, there's nothing to propagate. Okay, so it's an interesting paper still to read because they talk about the issues in actually getting a reasonable number of seed pages. Okay, where if you were to initialize their trust, then the propagation step will give non-zero trustworthiness to a large number of pages. If it doesn't, this idea is dead in the water. Right? Because then the reset matrix will still be epsilons for most of them except for the 5 pages that you said are trustworthy. And that's not going to be useful. Okay? Any questions on this?
And how can you trust on the hub?
What? No, all I am going to say, no, I did not say you should trust the hubs. I'm just saying, so there are 8 billion pages on the web, right? And you said, I have enough patience to manually label 100 pages, saying these are trustworthy, these are not trustworthy. Only 100 pages. Because after all, I assume you have other things to do in your life. Okay, which pages am I going to show you? If I show you my page and some other people's page, and you may say, yeah, I trust this, I don't trust this, I have no clue. Okay, but I used up all my 100 questions, and you go home, and now nothing is propagating. So what I should be showing you is the hub pages, and I ask you among the hub pages, which ones do you trust? So the idea is that you should be showing New York Times and Al Jazeera, or whatever, no, I don't know what a great Israeli, Hartal, I think. Hartal is one of the Israeli newspapers, and then Al Jazeera on the other side. And say, these are 2 hub sweats because they are pointing to lots of articles. Which one do you trust? If you trust both, that's fine. If you trust only one of them, that's very useful because then I will basically propagate. At least they have enough outlinks that I'm going to be propagating this. Okay, the question is not ask, if I ask a question and you answer it and it's, basically, and you're only going to answer 100 questions now because 100 pages you agree to classify. Human in the loop. Okay, so that was the point we made. Any other questions? Yes, sir.
The idea of looking at these like top 100 hubs, it seems to me like there's probably a low chance that any trusted sites at all would be in the top 100 hubs.
No, I know, but it's not even 100 anyway, right? It could be.
Well,
first of all, if you're doing it at a search engine size, right? Well, you probably have undergrads, that can be paid. Again, these are not, okay, when I say trustworthy here, really I mean reputation.
Well, you're talking about like Al Jazeera and stuff, or like, big sites that we would trust would not be anywhere close to the top hubs. The top hubs would be sites like Delicious or like Dig or something.
No. If you actually were to do authorities hubs computation, Al Jazeera would be both a authority and a hub in the high level.
Okay.
Because it has enough outgoing links and enough incoming links. Page rank wise, that is a problem.
Yeah.
Which is why page rank, you need this idea of inverse page rank, which sort of approximates the hubness. Do you see what I'm saying? Again, this is one more reason why you are happy to have heard about authorities hubs before, because you actually know the answer would have been hub score, and every page has both a hub score and authority score. Newspaper sites will have both authority and hub. Strong and silent types only have authority and no hubness because they are not pointing to anybody. Okay? Any other questions? Okay. So then I go back and do the Aardvark thing, which is basically, remember I was saying I was going to look at finding human sources. This we did now, which is analyzing trust and using the analyzed trust to set the reset matrix so that you can get a TrustRank, which is kind of a page rank sensitive to trust. Okay, and now of course TrustRank depends on the seed set and how the trust is propagated from there. Okay. We looked at that. Now I want to kind of say a few things about Aardvark, which is kind of a useful thing too. This is much more recent. So this site actually exists, but as they say, February 12, 2010, they got acquired by Google. So Google basically has Buzz, which they think that will be as big a social network as Facebook. Okay, I don't know about you. I shut off my Buzz right away because I was told that I already have 36 friends I'm following. And I didn't know who these people were. But, so anyway, so they are hoping Google basically bought this up because it could be useful. And what's the point here? In social search, the idea is you ask a question and you are going to take the answer only if it is from a trusted person. These are questions that have lots and lots of answers, but what matters is who is giving the answer. Messenger matters as much as the message. That's the way the normal life works, right? For example, I'm thinking of getting my roofing done. Who do I think I should look at? And, there may be many people who can do roof repair, but I'm likely to go with the one who my friend recommends because my friend just had it done and they were not too unhappy, so I'm just going to do that same thing. Okay, so what I'm looking for is people who will answer my question. So here is a search over people, not pages. Now, the tricky thing about people is there are two issues. One is, do they have the answer to your question? And the second is, would they bother giving the answer to you? Right? And the third, of course, related to it is, would you trust them? Okay? And the second and third questions are very much, based on the social network. If these people are connected to your friends or friends' friends or friends' friends' friends, you A, are more likely to trust them because somebody trusts them and they are in their social network. And B, they are also likely to basically take time off from whatever they are doing and give an answer to you. Okay, the first question of course is, do they have the competence to even do this, to even answer this question? That is important because basically what Aardvark tries to do is it's a mediator. What it does is when a question comes, so here is an example. So apparently some guy asked this question, where can I find a great half-day hike within a short drive of San Francisco, blah, 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 and life story of this person. And then Aardvark then, says, looks at some person who is in their social network, but probably a couple of hops away. So in this particular case, it says, I'm looking for someone in your network who knows about hiking now. Here I found Julia, who is in San Francisco, who is a friend of your friend Max Ventila. Now you wouldn't know Julia, because you essentially would be navigating the social network locally, so you only know your friends, you don't know your friends' friends normally. But Aardvark, on the other hand, has the access to the entire social network of the world. So it can very easily figure out who is connected to who in how many skips accounts. This can be done by Facebook. Actually, Facebook should be doing this too. Okay, so now of course, Julia would probably answer only because this is like, if this was a person who is a friend of yours, who unbeknownst to you, actually also has moved to San Francisco, 3 weeks back, right? Then you may not know this, and your friend has competence in answering this question, and obviously you would trust your friend's answer. Okay, and similarly, you will also sort of trust your friend's